नमस्कार दोस्तों, वेलकम टू गेट वाला। मैं हूं सतीश कुमार द्विशेट्टी, फैकल्टी ऑफ ऑप्टिकल इंस्ट्रूमेंटेशन। कैसे हो सब लोग? जल्दी से जल्दी ज्वाइन करो बेटा। आज हम डिस्कस करने वाला है ऑप्टिकल इंस्ट्रूमेंटेशन का महा रिवीजन। ओके, ऑप्टिकल इंस्ट्रूमेंटेशन एक छोटा सा सब्जेक्ट है। इसमें क्या क्या टॉपिक्स है, उसमें क्या क्या क्वेश्चंस आने वाले के चांसेस है, क्या क्या फॉर्मूलास है, वो भी हम डिस्कस करेंगे। ओके, सो जल्दी से जल्दी ज्वाइन करो बेटा। आज हमने ऑप्टिकल इंस्ट्रूमेंटेशन का लेक्चर में पूरा इंट्रोडक्शन से लास्ट टॉपिक तक सिलेबस का जो इंपॉर्टेंट टॉपिक्स है उसके ऊपर चर्चा करेंगे। सो ये सब्जेक्ट है ना, ये सब्जेक्ट इंस्ट्रूमेंटेशन के लिए कोर सब्जेक्ट है। कल हमने सेंसर्स एंड इंडस्ट्रियल इंस्ट्रूमेंटेशन पढ़ चुका है, आज ऑप्टिकल इंस्ट्रूमेंटेशन पढ़ रहे हैं। ओके, सो ऑप्टिकल इंस्ट्रूमेंटेशन में क्या क्या टॉपिक्स है, उसमें क्या क्या इंपॉर्टेंट एरियाज है। आईएन बच्चों के लिए ये ओल्ड सब्जेक्ट है, लेकिन डबल ई स्टूडेंट्स के लिए नया सब्जेक्ट है। ओके, सो जल्दी से जल्दी ज्वाइन करो बेटा। एनीबडी इज देयर फ्रॉम डबल ई इंस्ट्रूमेंटेशन? प्लीज टाइप देयर। ऑडियो वीडियो सब कुछ क्लियर है? मुझे एक बार कंफर्मेशन कर दीजिए बेटा। इज ऑडियो वीडियो इज क्लियर? यस। चलो माय डियर, तो आज हमने ऑप्टिकल इंस्ट्रूमेंटेशन में क्या क्या टॉपिक्स डिस्कस करने वाले हैं। एक बार देखो, जो टॉपिक्स हमने डिस्कस करने वाला है, ऑप्टिकल इंस्ट्रूमेंटेशन का सिलेबस बहुत छोटा सा सिलेबस है। ओके, ऑप्टिकल इंस्ट्रूमेंटेशन का सिलेबस बहुत छोटा सा सिलेबस है। जस्ट विल हैव बेसिक ग्लिम्स, बट इट इज वन ऑफ द इंपॉर्टेंट एरिया। सो फर्स्ट वी आर हैविंग द ऑप्टिकल सोर्सेस। Optical sources like LED and laser, etc. Optical detectors, like LDR and photodiode, etc. Next, fiber optics. Next, interferometry. Next, spectrometry. So these are the topics. एक बार समराइज करो बेटा। नहीं होगा माइक्रोप्रोसेसर का। प्लीज नोट डाउन दिस टॉपिक्स। मेजरमेंट्स का सब कुछ हो जाएगा ना, मेजरमेंट्स का भी एक आएगा, सेशन आएगा, डोंट वरी। कल का सेशन कितने लोग देखा? सेंसर्स एंड इंडस्ट्रियल इंस्ट्रूमेंटेशन का सेशन कितने लोग देखा कल का? हाउ मेनी ऑफ यू वॉच्ड द यस्टरडे सेशन सेंसर्स एंड इंडस्ट्रियल इंस्ट्रूमेंटेशन? Because almost like 2.5 hours I took the session, 2 hours or 2 hours plus, but I was able to see only 9 or 11 students because instrumentation का जो subject है, so very number of aspirants are less. But when the EE people and EC people are writing this paper, so for those students these subjects are compulsory rank predicted subjects, because how much you score in these subjects, based on that only your rank is going to be guessed. Okay, is it clear, my dear? Yeah. Chalo. So first let us start the topic, optical sources. So let us start this topic first, optical sources. Okay, optical sources में, optical sources is a topic which discusses about majorly how the light is going to be generated. Light generate होने के लिए क्या क्या possibilities है दुनिया में. Okay, so light is possible by concepts like incandescence, next, what is incandescence? Incandescence means generation of the light due to heat. Incandescence बोलो तो क्या है? Generation of the light due to heat. Generation of the light due to heat. So examples क्या क्या आएगा उसमें? Examples है sunlight, candle, tungsten filament bulb. Okay, tungsten filament bulb. Next, the second one is the fluorescence. Sorry, luminescence. Luminescence. इसमें क्या क्या आएगा? This luminescence is a generation of the light without heat. Generation of the light without heat majorly. Okay. Yes, there is no other option. Manvind Yadav. Instrumentation control engineering, electronics का ही पार्ट क्या है? गुरुजी फॉर रिक्वायरमेंट्स पर्पस इन हरियाणा. एनालॉग डिजिटल कंट्रोल्स ये सब कुछ पढ़ना है. अनिल सोनी, आपने कल का सेशन देखा? जयदीप, कल का सेशन देखा आपने? जितने लोग हैं, पुण्य भरता दिंदा, आपने कल का सेशन देखा सेंसर्स एंड इंस्ट्रूमेंटेशन का? एक बार देखो, कल का सेशन भी देखो सेंसर्स एंड इंस्ट्रूमेंटेशन का. So this luminescence, so under the natural luminescence, example will be like fireflies. Under the chemical luminescence, mixture of two chemicals. Luminol plus H2O2, when they mix, there is a blue color, light will come. Next, electric luminescence, the best example is LED, light emitting diode. So LED is one of the important area where one can get expect a question. Okay, so please make a note of these points. Is it corona? నాకు ఏ పరీక్ష క్లాస్ లేకపోతే So first we'll talk about LED. Is it clear, all of you? Please reply me. All of you noted? Yeah. Let us start some points about LED. Next comes the LED. LED is called as light emitting diode. Light emitting diode is a forward bias diode like this. So when the bias current travels, so this is a DC voltage, so there is a possibility of light emission. So the materials used are majorly gallium arsenic, gallium indium arsenic, majorly. Make a note of these points. It's a forward bias, forward biased. Materials. This LED light emission is not possible in all semiconductors, so they are called as direct band gap materials. Direct band gap materials. The basic concept of LED is there is an energy band like this. This is a E1, this is a E2, and this is an energy gap, that is E2 minus E1. So these are the electrons waiting for the energy. Okay, so in the first step, that is what we call as absorption. When you give some input bias voltage, the bias current is taken as an input, which gives the kinetic energy. So by taking this kinetic energy, these electrons are going to jump. These electrons are going to jump. So now these electrons will move here, so forming certain holes here. So in absorption, electron hole pair combination will be taking place. But remember, for the emission of the light, electron hole pair combination is not the matter. For emission of light, electron hole pair recombination is the matter. No, I don't think so, Rohan. They are having measurements. Okay, continue whatever you heard. कल का सेशन कैसा लगा सोहन जी? So this is the electron hole pair absorption, electron hole pair combination. So what is going to happen here? Electron hole pair combination. My question here is, electron hole pair combination does not give you the light. Am I right or not? बहुत लेस टाइम में मैंने पूरा कंटेंट दिया है कभी, और अब ऑब्जर्व हमने मैं 4-5 सब्जेक्ट्स ले रहा हूँ, सेंसर्स एंड इंस्ट्रूमेंटेशन, ऑप्टिकल इंस्ट्रूमेंटेशन, नेक्स्ट COA सब्जेक्ट एंड मेजरमेंट्स, 4 सब्जेक्ट्स का वहाँ रिविजन आएगा, इसलिए 2-2 घंटे 2 आवर्स का सेशन ले रहा हूँ मैंने. तो वंस it reaches to the higher energy level, once it reaches to the higher energy level, in the higher energy level the electron cannot wait for longer time. So these are the electrons. So this is the E1 state, this is the E2 state, this is the energy gap, the E2 minus E1. So now second step here is, the lifetime here is 10 to the power of minus 8 seconds. Once the lifetime is crossing this 10 to the power of minus 8 seconds, so these electrons will come back, they will fall down without any external stimulus, according to their own. एक बार lifetime होने के बाद वो नीचे आएगा. So whenever they are coming down, what happens? Whenever they are coming down, जो कुछ एनर्जी लेके ऊपर गया ना, वो पूरा सा एनर्जी नीचे डालना है in the form of light. So this is what we call as emission, and especially this emission को हम बोलते हैं spontaneous emission. Spontaneous emission बोलते हैं. ओके, ये spontaneous emission की वजह से क्या होगा, जो कुछ एनर्जी, this is released in the form of light, this is a light of wavelength. So energy of the photon will be equal to energy gap. So this energy of the photon is nothing but energy gap, that is E2 minus E1 electron volts. Energy of the photon is hc by lambda, so this is energy gap. So the lambda of the light which is released will be the formula. So this is a lambda of light, is an expected question. Please note down. Noted, my dear? Noted, my dear, this one. So this is an expected question. So lambda of the light emitted is given by hc by energy gap in electron volts. Compulsory, this energy gap should be electron volts. So what is this h? H is called Planck's coefficient or Planck's constant. H is called Planck's constant. So H का वैल्यू कितना है? That is 6.625 into 10 to the power minus 34 joule second, or 6.625 into 10 to the power minus 27 ergs second, or 4.14 into 10 to the power minus 15 electron volt second. So this is the value that we will take in the numerical problems. Okay, so now C is the velocity of light, 3 into 10 power 8 meter per second, which is the velocity of light. So now if you see, check the units, H ka units you have to take in electron volt second, C ka units meter per second, energy gap ka units electron volts, electrons is cancel, seconds cancel, so lambda will be in meters. So for example, if you take for a semiconductor material of energy gap 2 electron volts, find the emission wavelength. Try to do it. Try to do it. What is the answer? Please tell me fast. आंसर बताइए बेटा. So energy of the photon will be obviously equal to energy gap. Energy of the photon is equal to hc by lambda, that is equal to energy gap in electron volts. So lambda is equal to hc by energy gap in electron volts. H का वैल्यू कितना है? 4.14 into 10 to the power of minus 15 electron volt second into C का वैल्यू 3 into 10 power 8 meter per second. Next, energy gap is 2 electron volts. So now यहाँ से आपको ये कट हो जाएगा, seconds कट हो जाएगा. So this is 2.07. okay, 6.21. तो राइट कितना आ रहा है? 6.21 into 10 to the power minus 7 meters. So कितना आ रहा है? If you take 621 nanometers, it's a green, it's a blue color light. Expected question. ओके चलो let us go for the next question. So if you take the LED, in LED what we are giving, we are injecting the number of EHP's electron hole pairs, we are injecting and number of photons are emitted. So quantum efficiency of LED which is called as internal quantum efficiency. What we call this as internal. It means light is generated internal inside the LED. So how many number of photons emitted divided by number of EHPs injected. Number of EHPs injected. So please make a note of these points here. Focus on the class, okay? So internal quantum efficiency is given as number of photons emitted by number of electron hole pairs injected. कितना दिया आपने in the form of the bias current, आपने bias current दे रहे LED को, वो bias current की वजह से क्या होगा, bottom से ऊपर तक थोड़ा सा electron hole pair inject हो रहा है. It is not guaranteed that each and every electron hole pair which is jumping from the higher to lower should emit the light. That depends upon the energy levels of that electron. Out of 100 electrons which are jumping from the lower to higher, and similarly when the 100 electrons when they are jumping from the higher to lower, it's not guaranteed that 100 photons should be released. That depends upon their energy level. Some of the electrons may not be that much active. Okay, so number of photons emitted. Suppose if you take this as number of photons per time, if you take number of EHPs per time, if you take per time, and if you take quantum efficiency as a percentage, you want a percentage, it should be multiplied with 100. So this is what we call as rate of photons divided by rate of EHPs. So this is the internal quantum efficiency formula. So rate of photons is what? Rate of photons. Rate of photons means the units should be per second. Rate of photons is defined as how much optical energy is emitted internally divided by energy of the photon. Power is equal to energy per time, so energy gets cancelled, per time you are going to get. Next, rate of EHP means what? This is also unit should get per second, so I bias divided by charge of electron. So please make a note of these points. కూర్చోబో ఇస్తా అక్కడ పెట్టినాడు వాటర్ అక్కడ పెట్టి చెప్పుల okay, taken these expressions, all of you taken these expressions. It's not a part of electronic. It's not a part of electronics. It is for 𝐂𝐸𝐼𝑛. If you are writing the 𝐂𝐸𝐼𝑛 paper, if you're writing the 𝐂𝐸𝐼𝑛 paper. Okay, all of you noted, my dear? So this is a quantum efficiency ka formula. So if you write this quantum efficiency full form, so which is called the internal quantum efficiency, internal quantum efficiency. This is what we call as internal. This is what we call as internal. Okay. So internal quantum efficiency is given by rate of photons divided by rate of EHP. The rate of photons formula, P optical by energy of the photon, the whole divided by I by. So if you take this expression and if you see this part, how much optical power is coming for how much current you are giving. So this is a current entering to the diode and how much optical power is generated internally. How much optical power is generated internally. Okay, so now if you check P optical by I by S, how much optical power is generated internally. Understood? So this ratio, if you check this P optical, that is what we call as responsivity of LED, responsivity of LED, that is RE, that is equal to optical power by I by S. Please note down, the units are microwatts per ampere. So these are the most expected questions from the LED. Note down. Class. Noted? That's it. This is all about the LED. Okay, noted. The next topic in optical sources is the laser. What is the laser full form? लेजर का फुल फॉर्म क्या है? लाइट एम्प्लीफिकेशन by stimulated emission of radiation. So that is the topic. Please note down. Light amplification by stimulated emission of radiation. So as the name indicates, it is not a spontaneous emission, it is a stimulated emission. It is what emission? It is a stimulated emission. What do you mean by stimulated emission, and what is the fundamental difference between spontaneous emission and stimulated emission? If you see, these are the energy band. So this is a E1, this is a E2. So this is a energy gap, E2 minus E1 electron volts. Electrons are waiting for the energy. Electrons are waiting for the energy. So first step is same. First step is absorption. In absorption, we are giving some input. By taking this input, these electrons will go up. So now the electrons will be moving up, so holes will be forming here. So in absorption, what is going to happen? Electron hole pair combination is going to happen. Okay. So previously, either it is a LED case or it is a laser case, हमको लाइट बाहर निकालने के लिए हमको इलेक्ट्रॉन होल पेयर कॉम्बिनेशन नहीं है, इलेक्ट्रॉन होल पेयर रिकॉम्बिनेशन होना है. Recombination बोलो तो electron should jump from the higher energy level to lower energy level. So in spontaneous emission, the electron will wait up to 10⁻⁸ seconds in the higher energy level. वो पूरा टाइम होने के बाद it will jump from the higher to lower. Okay, but here the lifetime is 10⁻⁸ seconds. So before the 10⁻⁸ seconds itself, before the 10⁻⁸ seconds itself, if an externally triggered photon is hitting, if an external photon is hitting, then what happens? This will fall down. This will fall down. So whenever it is falling down now, then what happens now? There will be two photons to each other. One is our hitting photon, is the hitting, and this is the photon due to E2 minus E1. Okay, so which is the two photons? This is the E1 and this is the E2 energy gap. So the hitting photon and the hidden photon, you understand? Hitting photon and the hidden photon together will come. So this hitting and hidden photon, we can say hidden So now when they are coming togetherness, the light which is coming is together light. So this emission is not happening spontaneously. This emission is happening because of, G. This emission is it spontaneous? No. This emission is not happening because of waiting up to 10⁻⁸ seconds then free fall. No. Before the lifetime, if an external photon comes and triggers to the external, then it is going to down. So this is what we call as emission, which is called the stimulated emission. What we call this as, this is what we call as stimulated emission. Spontaneous emission nahi hai, stimulated emission hai. And the properties of stimulated emission are, features of stimulated emission, if you see the features of stimulated emissions, if you check, they are coherent, single phase. Single phase means they are coherent. Next, single wavelength. इसको हम बोलते हैं मोनोक्रोमैटिक. Next, the last but not the least, single direction. Single direction means it is called focusing, directionality. So these are the features of the laser light, and also called features of laser light. Laser light is highly coherent. Laser light is highly monochromatic. Laser light is highly directional. Understood, my dear? दीक्षा जायसवाल कैसे हो? So to perform this laser, it's not that much easy. आपको फ्री में ऐसा नहीं मिलेगा. आपको एलईडी में, एलईडी के लिए एक मटेरियल है गैलियम आर्सेनिक. गैलियम आर्सेनिक को जस्ट यू आर गिविंग सम 2 less than 2 amperes of current, then your milliamperes, not even amperes, milliamperes of current if you give, the LED light will glow. But whereas a laser, how the laser can be generated? How the laser can be generated? So laser के लिए कुछ requirements है. Okay, so the requirements of laser, let us take. So the laser requirements, if you see, लेजर के लिए क्या क्या रिक्वायरमेंट्स है. फर्स्ट, द लेजर के लिए एक मीडियम चाहिए, देन पॉपुलेशन इन्वर्शन चाहिए एंड ऑप्टिकल रेजोनेटर्स चाहिए. तो फर्स्ट वी नीड active gain medium, optical resonators. This is what we call as first one, active gain medium. The first requirement. The second requirement is the population inversion. And the third requirement is optical resonators. So ये है 3 रिक्वायरमेंट्स है. लेजर जनरेट करने के लिए आपके पास एक मीडियम होना है. उसके बाद लेजर जनरेट करने के लिए कंडीशन होना चाहिए. सौरमंडल कैसे हो भैया? So आपको लेजर कहाँ जनरेट होता है? So they based upon the their mediums. अगर लेजर is possible in solids, laser is possible in liquids, laser is possible in gases also. If the laser is happening in solids, then it is called solid state laser. If the laser is happening in the liquids, then it is called liquid state laser. If the laser is happening in the gases, then it is called gaseous state laser. The example for solid state laser, can you give me an example? Similarly, the example for liquid state laser, any example? Similarly, the example for gaseous state laser. I will give you the example for gaseous state laser. There is a helium neon, CO2, argon. These are the gaseous state laser. That means the laser action is going to take place okay. चलो, so gaseous state laser में क्या क्या आएगा? Helium neon laser, argon laser, CO2 laser. The most efficient laser till today, is a helium neon laser. And अगर CO2 laser देखो तो CO2 laser is used in the metal cutting, welding, in a welding operations, in cutting operations will use the CO2 laser. Next, liquid state laser. Liquid state lasers में आपको dye solutions आएगा. Is not as successful till today, but this is most successful. Okay, so this is most successful. Helium neon laser, dye solutions. Solid state lasers में आपको क्या क्या आएगा? Ruby laser, ND-YAZ laser, semiconductor laser. So these are the examples. Please note down. Solid state lasers में, that means solid medium like crystals. Some crystals are going to generate the laser. Example है ruby laser. ND-YAZ means niobium, yttrium, aluminum, garnet. Niobium, yttrium, aluminum, garnet. This is a crystal. SC means semiconductor. Liquid state laser में आपको dye laser आएगा. Gaseous state laser में आपको मिलेगा helium neon, CO2 and argon laser. So these are the basic things. Just like LED में आपको कुछ material है like gallium arsenic, gallium indium arsenic. Similarly here also laser generate करने के लिए भी आपको कुछ medium चाहिए. अगर वो medium solid है तो उसको solid state laser बोलते हैं. Example ruby laser. अगर गैस में लेजर जनरेशन हो रहा है उसको गैसियस स्टेट लेजर बोलते हैं. एग्जांपल हीलियम नियन लेजर. अगर लिक्विड्स में भी कुछ केमिकल रिएक्शन, एडिंग वन केमिकल लिक्विड टू अनदर केमिकल लिक्विड लेजर इज पॉसिबल, उसको हम बोलते हैं लिक्विड स्टेट लेजर. ओके, सो दिस इज द फर्स्ट थिंग. एंड द सेकंड मोस्ट इंपॉर्टेंट थिंग इज बाय डिफॉल्ट जनरली इन एनी लाइट emission concept the number of electrons in the lower energy level is greater than the number of electrons in the second energy level. ऐसा not by default all the electrons will be waiting at the ground state. लेकिन ये particular condition आपको लेजर के लिए सपोर्ट नहीं करेगा. लेजर के लिए क्या है ना, लेजर के लिए इधर इलेक्ट्रॉन ज़्यादा होना चाहिए. लेजर के लिए इधर इलेक्ट्रॉन्स ज़्यादा होना चाहिए. So that is what we call as population inversion. So we have to achieve the population inversion. So the population inversion को हम बोलते हैं number of electrons in the higher energy level state must be more than number of electrons in the lower energy level. This is what we call as population inversion. And this population inversion was invented by the Albert Einstein. And this population inversion is achieved by a process called pumping process. So by using the pumping process, we are lifting all the ground state electrons to the higher energy level, so that by the time our excited photon comes and hits, a bunch of electrons are available at the higher energy level. So once the triggering photon comes and hits this group of electrons which are already settled at the higher energy level, a lot of collisions will take place, bombarded, and the laser is going to be taken place. To achieve a highly efficient laser, N1 greater than N2 is not the possible condition. To achieve a high efficient laser, N2 greater than N1 is a best sufficient condition. Number of electrons staying at the higher energy level should be more than the number of electrons in the lower energy level. उसको हम बोलते हैं population inversion. The process of achieving the population inversion is called pumping process. The process of achieving the population inversion is called pumping process. So what type of pumping you are going to use? So pumping, if you check for liquids, for solids, and these different pumping techniques are there. Can anybody tell me? For solids we are using optical pumping for solids. For liquids we are using the chemical pumping. Okay, and for gases we will be using the electric discharge pumping. Electric discharge pumping. So this is for gases. Please note down this. Optical pumping is possible in solids. Liquid pumping is possible in chemical. Gaseous state laser is coming from the electric discharge. Is it clear, my dear? And the next most important thing is the optical resonators. एक बार light generate होने के बाद आपको एक set of resonators है. So between the set of resonators, when the light is traveling, this is a set of resonators. So all of you are following up to now? All of you followed, my dear? Diksha ji, Sauro Mandal ji, Himanshu, Rohan, Anil Soni, Jaideep ji, Punya Bartha Dinda ji, Anil Soni Dhupar. Clear? I think Diksha Jaiswal, you are not from the instrumentation background. Saurav Mandal, you are from Triple E, right? Yeah. So what is this resonators? So these resonators are like this. There is a mirror which is 100% reflective, and there is another mirror. Yeah. So this is 100% reflective type. Let us take this as a mirror 1, this is a mirror 2, this is a mirror 1. So this is a cavity. So this mirror 2 is 100% reflective. Mirror 1 is partially lifted. This is partial. Okay. And the length of this cavity, I can take it as L. From this point to this point, the length I am taking it as L. Cavity length L. So now what happens now here? First, one pair of photons is generated in the medium. When the electrons are jumping from the higher energy level to lower energy level, before the lifetime when the excited photon hits, okay, so triggered photon and hidden photon both are together is coming, so the light is going to be generated. So now the photon is going to come like this. It hits here, but it's 100% reflective. So again this path, by the time it comes here, there is another photon pair may be ready. So that photon pair may be interfere here. When two photon pairs are interfering, then what happened? The resultant will be more amplified light. Out of that amplified light, some portion of the light will be going out. Try to understand this point. First one photonic pair is released. So this is one photonic pair released. So this is the first photonic pair. So this is the first photonic pair. Why I am using the word pair? Triggering photon, hidden photon. Triggering photon is excited photon. Hidden photon is from E2 to E1, that photon. These two photons are coming together. So now this both will be coming like this, traveling a distance L, cavity length L, and touches this mirror. This mirror is 100% reflective type. Then what happens? This particular photon will be coming back. Now tell me, this particular photonic pair has traveled how much distance now? How much distance it's traveled? It has traveled a distance of 2L. So by the time second photon pair exists, the first photon pair has traveled how much distance? Please answer. My dear students, optical is not that much easy as you think. Optical is the greatest subject. Optical is all about the light. For me, light बोलो तो सूर्य भगवान, light बोलो तो life है. Don't think optical is such an easy subject. Very, very important concepts. It's electromagnetic wave. Answer. I'm waiting for answer. By the time second photon pair comes into existence, the first photon pair has traveled how much distance? यार क्वेश्चन समझ में आया आपको? सौरमंडल जी, एक फोटोनिक पेयर ऐसा जनरेट हो गया इधर. फोटोन पेयर क्यों यूज कर रहा हूं मैंने? सी हियर दिस पिक्चर. हियर जो हो रहा है ना, दिस इज द फोटोनिक पेयर. काजल, शाहरुख खान टुगेदर. शाहरुख इज एक्साइटेड, काजल is hidden together. A pair बन गया. काजल is waiting at the ground floor. खाना होने के बाद रात में, कुछ खाना पीना होने के बाद रात में एग्जिट होके टेरेस के ऊपर आ गया. Once she comes to the terrace, our hero काजल टिन will come. Both will trigger. दोनों पेयर बना के बाहर चलेगा. समझ में आपको? pair ban gaya. So now imagine a medium in which millions and millions of pairs of photons are going to be generated. So the first pair of photon, once it is generated, the first photon pair, once it is generated, once the first photon pair is generated and traveling a distance L, hitting the mirror which is 100% reflecting and coming back, by the time another photonic pair came. So what is the difference between the distance traveled by the first photonic pair and the second photonic pair? That's my question. I am expecting this answer. Before the second photonic pair comes into picture, the first photonic pair is traveled how much distance? Excellent Diksha ji, 2L. समझ गया आपको? स्टोरी समझ गया? So I am a pair, I am traveling a distance L, hitting the mirror, coming back 2L. Now another photonic pair is added on me. Already I am having an amplitude of A1 plus A2, Kajal plus Shahrukh Khan, and another photonic pair is newly born A3 plus A4 amplitude. So net amplitude is A1 plus A2 plus A3 plus A4, amplified light बन गया. लेकिन प्रॉब्लम क्या है? ये एम्प्लीफिकेशन कब कंस्ट्रक्टिव होता, कब डिस्ट्रक्टिव होता? That depends upon the distance difference. If the optical path difference, see the word optical path difference. अरे यार, by the time second photonic pair पैदा होने के समय में ये first photonic pair has completed distance 2L exactly, and it is now exactly covered 2L, and then the second photonic pair is hitting, then the difference between them is 2L, that is an integer multiple of lambda. Then a constructive interference is going to happen. When constructive interference is going to happen, first two photons and next two photons together, the net amplitude will be more increase. You understand, my dear? So that is what we call as an expression, the optical path difference. What we call this as optical path difference. The optical path difference is 2L. So condition for constructive interference, condition for constructive interference, all of you understanding, my dear? All of you understanding, Diksha ji, Saurav Mandal, Rohan? Condition for constructive interference क्या है? Condition for constructive interference क्या है? The optical path difference must be equal to integer multiple of lambda. So here the optical path difference is 2L, so 2L is equal to n lambda. So now what is the frequency of the laser? Frequency of the laser is equal to velocity is equal to distance by time. Velocity is equal to distance by time, 1 by d into frequency. So frequency is equal to v by d. C is equal to frequency into lambda, na? Laser frequency क्या होगा? Frequency of the laser. Frequency is equal to velocity is equal to distance by time. Velocity is equal to distance into 1 by time. 1 by time means frequency. Frequency means C by. So this is the frequency of laser. Note down. Now, if this is a gaseous laser, it is not for the electrical students. If you are writing the instrumentation gate paper only, okay. Suppose if the medium is not gas, if the medium is solid, then the frequency of solid lasers, that is C by 2 mu L, where mu is the refractive index. Is it clear? Chalo. Clear? So these are some points about the laser. Chalo. Now let us go for differences between LED light laser light. Okay, let us take the differences between LED and laser. Okay, leave it. Leave this, no problem. That is the problem I'm telling now. Many of the students, they don't know the subject is for what. Chalo. LED works on the concept of spontaneous emission. This is stimulated emission. This works on the concept of spontaneous. This works on the concept of stimulated emission. The materials are gallium arsenic. Here the materials will be gases, liquids, solids. It is low power consumption. It is high power consumption. So this is non-coherent, incoherent or non-coherent light. This is coherent light. This is non-monochromatic. This is monochromatic. This is dispersive light. This is directional light. Focusing. Understood? It's not a powerful light. It is powerful. It can cut the metals also. The dispersive angle is more, theta d. Angle of divergence is more. The angle of divergence is less. It's called angle of divergence. Okay, my dear. So these are the major features of the laser. How many of you are following? Please give me the response. कोई जिंदा है? बहुत डिफिकल्ट है भैया टीचिंग द इंस्ट्रूमेंटेशन सब्जेक्ट्स फॉर ए क्राउड वेयर नोबडी विल बी देयर इन द लाइव क्लास. वेरी डिफिकल्ट. Nobody is responding also. रोहन जी किधर हो? That's why I very rarely I will ask this revision classes because live app students के लिए बहुत बहुत easy है. देखो वो रेस्पॉन्स डिफिकल्ट लेवल रेस्पॉन्स. ₹40 తీసుకుంటాడు తెలుసు కదా లోపల మొత్తం. స్లోగా తగ్గుతుంది 2-3 days పడుతుందని చెప్పి. ఈరోజు అయితే డే మొత్తం ఫీవర్ లేదు కదా. లైవ్ చూద్దాం. चलो let us move for the next optical detectors. यस केशव जी, ऑप्टिकल डिटेक्टर्स बोले तो क्या है? ऑप्टिकल डिटेक्टर क्या करेगा? ऑप्टिकल डिटेक्टर का इनपुट क्या है, आउटपुट क्या है? द इनपुट इज ऑप्टिकल लाइट, output is electrical output. It is just opposite to the optical source. LED is optical source, photodiode is optical detector. Okay, so the best example I will give you, photodiode. Photodiode is the best for visible radiation detector. Visible radiation detector. Live app, you purchase the live app from the PW. The photodiode and LDR, these both are the visible radiation detectors. So first let us take the LDR. LDR stands for light dependent resistor. As the intensity of the light increases, the resistance of the LDR decreases. So this LDR is a material like this. LDR, and this LDR surface you can see. So when the light falls on it, its resistance decreases. So if you see the graph, as the intensity of the light increases, the resistance of the LDR decreases exponentially. If you are following, so when there is no light, zero light, the resistance is in kilo ohms. So this is what we call as dark resistance. And under the maximum light, so this is the shine resistance. So which materials we are using for LDR? If we check, cadmium sulfide, cadmium selenide, lead sulfide, lead selenide, lead telluride. So these are the materials of the LDR. Make a note of these points. So this cadmium series is best detector for visible radiation, and this is for IR radiation also. Note in a question, wait. Yeah. Now note the question. A LDR which is initially at dark conditions has been as exposed suddenly to a light, which is initially dark conditions has a resistance of 100 kilo ohms, suddenly exposed to a light source. Under the maximum illumination, okay, under the maximum illumination, the resistance becomes as 80 ohms, not 80 ohms, let us take 1 kilo ohm. What is the resistance of LDR just after 80 milliseconds of light focusing? What is the resistance of LDR just after 80 milliseconds of light focusing? The time constant of LDR is given as 150 milliseconds. So what is the answer? Please try to do it. Try to do it. 𝐂𝐤𝐬𝐞, try to do it. Whoever are there in the live, एक बार thumbs up दिखाइए बेटा. Okay. Anybody? जितने लोग लाइव में हैं मुझे एक बार थम्स अप दिखाइए बेटा. How to do this problem? The LDR, which is initially dark conditions, has a dark resistance of 100 kilo ohms. So if you see the problem, so this is the way you have to do this. This is the way you have to do it. So this is our zero light. This is a maximum light. So this is a light on x-axis, on y-axis resistance. At zero light, the dark resistance was how much? 100 kilo ohms. Okay, so that is a point you have to understand. Just from the given information I am taking the data. Under the maximum illumination, the resistance of the LDR becomes as 1 kilo ohm. And if you see the first order system, the time constant of the LDR is given as 150 milliseconds. Is asking what is the resistance of the LDR at a particular time. Asking. So how to do this? If you see, this is a capacitor discharging type curve. So resistance at a final, that means infinite, is equal to resistance at initial. How to do this problem? I think you have aware of this. Resistance at a particular time. How to do this? Capacitor discharging curve formula. Resistance at a particular time is equal to resistance at final, which is infinite, plus resistance initial 0 minus resistance at final infinite into e power minus t by 2. So that is expression. Just like voltage across the capacitor at a particular time is equal to final voltage at infinite time, initial voltage at 0 time minus final voltage at infinite time into e power minus 2, like this. Similarly here, what is the resistance at final? That is sign resistance, that is 1 kilo. What is the initial resistance? That is the dark resistance, so I will take it as 100 kilo ohms. And final resistance 1 kilo ohm. Just after 80 milliseconds of light focusing time, this is 150 milliseconds. Now you can find out the resistance at a particular time. Please solve it and tell me. What is the answer? 0.59. No, wrong. What is the final resistance here? Oh, 100K ना. Okay, okay. Calculate करके बताइए. Use the 𝐂𝐤𝐴. Milliseconds gets cancelled. E power take the exponential minus 8 divided by 15 into 99 plus 1. 59.07 kilo ohms na? Yes, 59.0. Chalo, let us move for the next topic, photodiode. Photodiode is a reverse bias photojunction. So what is photodiode? The photodiode is a reverse bias diode upon which you are going to get the photocurrent. So this is a bias. So now when the light is incident here, so you are going to get the photocurrent. So for the photodiode, we are giving input as light, input is light, output is photocurrent. So photodiode is what? Photodiode is a reverse bias PN junction diode. Reverse biased PN junction diode. Yes, correct only na? Yes, Keshav. So now if you see in photodiode what is going to happen. So these are the semiconductor layer. So this is a E1, this is a E2, electrons are here, they are waiting for the energy. This is the energy gap, E2 minus E1. Now a photon is incident on the ground level. So this is the energy of the photon. If energy of the photon is more than the energy gap, then what happens? This electron is already waiting for the energy. It's want to jump from lower to higher energy level. But if we want to jump from lower energy to higher energy level, it needs certain energy. Now the light is having a wavelength. Because of wavelength, the light is having some energy. If energy of this photon light is more than energy gap, energy of the photon is hc by lambda, so which is greater than energy gap, then if you take the lambda is less than hc by energy gap, it's electron volts. So as long as this particular condition matches, that means the light which is incident on the photodiode should have a wavelength in the range of less than hc by Eg. Do you understand this? What do you understand? That means as long as the incident light is having a wavelength which is less than this, then only, suppose energy gap is 2 electron volts, H is called 4.14 and C is something. So the instant light should be less than that. That means it can be a group of wavelengths below with the cutoff wavelength. Then that light can hit. Suppose if it is more than that wavelength, the lambda is increasing. If the lambda is increasing, the energy is decreasing. Remember this point, energy is inversely proportional to lambda. Yes, there will be a range of wavelength. Okay, you understand? There is a range of wavelengths for which the light should be incident. Within this range only the photodiode can respond. अगर एक लाइट का वेवलेंथ इससे ज़्यादा है, then that particular light cannot trigger the ground state electrons, because as lambda is increasing, energy is decreasing. If energy is decreasing, you cannot excite me. So this is what we call as spectral response. तो हम क्या बोलते हैं? Spectral response. The range of wavelengths within which the photodiode can respond. So the lambda is a range. Okay, the lambda is equal to hc by Eg. If I mention, then this is what we call as upper cutoff wavelength. This is what we call a spectral response. So now if you see the photodiode, then it jumps. The more is the number of photons incident for a photodiode. If you check, number of photons incident, the number of EHPs are released. So the quantum efficiency of the photodiode, PhD means photodiode, how many number of EHPs are generated how many number of photons incident. If you take it as a percentage, you have to multiply with 100. So the quantum efficiency of PhD, if you take number of EHPs per time divided by number of photons per time, that is called rate of EHP. This is what we call as rate of photons. This topic is quantum efficiency. Chalo. Is it clear? Quantum efficiency. I'm not going anywhere. Quantum efficiency is given. So now the quantum efficiency of the photodiode, the rate of electron hole pair generated divided by rate of photons. So rate of electron hole pair is given as how much photocurrent is generated, IPH divided by Q. The units are per second. Rate of photons is given as optical energy per energy of the photon. The units are per second. So now if you check the quantum efficiency of the photodiode, rate of EHP is given as IPH by Q, the whole divided by P optical by energy of the photon, which comes as IPH by Q EPH by P optical. So this is the quantum efficiency of the photodiode. And if you see this one, this IPH by P optical, that is what we call as responsivity. Photocurrent generated or optical power incident. Is what we call as responsivity. Let's note down these expressions. How many of you are satisfied by my session, today's session? Enough for today? These are the major areas you focus. Okay. If you have any doubts, you can ask me. Anybody any doubts, you can ask me.